This video covers all of Chapter 6. We're going to go over the kinds of organic reactions, reaction mechanisms, radical and polar reactions. We'll do an example of a polar reaction. We'll talk about using curved arrows, and then we'll move on to describing a reaction in terms of equilibria rates and energy changes. We'll discuss bond association energies, energy diagrams, intermediates, and then finally we'll compare biological reactions and lab reactions. There are four main types of organic reactions. The first two are shown here, addition and elimination reactions. In addition reactions, two reactants combine to form a single product. So here we have two reactants and one product. In an elimination reaction, a single reactant splits into two products, so that's the reverse of the addition. So here we have one reactant, and now we have two products. Another type of reaction is a substitution. In this, two reactants are exchanging parts to form two new products. Here you can see in green the O-methyl portion is being replaced by the OH portion from water to form acetic acid, a carboxylic acid, and an alcohol, methanol. In a rearrangement reaction, a single reactant is reorganizing its bonds and atoms to form an isomeric product. So if we look at this example starting with dihydroxyacetone phosphate, that can rearrange to form glyceraldehyde 3-phosphate, and these are isomeric products. Notice that here you have the double bond to oxygen, but now it's on the terminal carbon in the product. And likewise, the placement of the OH group has also changed from the terminal carbon to the middle carbon. Reactions occur through what we call reaction mechanisms. A reaction mechanism is the overall description of a reaction process, and it's going to describe how the electrons are flowing and how bonds are breaking and bonds are being made. And reactions will occur in defined steps that lead from reactant to product. So bonds can be formed and broken symmetrically or unsymmetrically. If there's symmetrical cleavage, we call that homolytic bond breakage or formation. If there's unsymmetrical cleavage, we call that heterolytic. So symmetrical bond breaking is shown here. If you have a bond between A and B, and then that bond breaks with each atom taking an electron, that would be symmetrical cleavage. And this leads to what are called radical products, which have unpaired electrons. Now in unsymmetrical bond breaking, you have again a bond between A and B, but both electrons are leaving with one of the two atoms to form A plus and then B minus. This is also a polar type of bond breaking. And this is the much more common type of bond breaking and bond forming that we will see in organic chemistry. So this is the bond breaking, and then this shows how those types of heterolytic or homolytic mechanisms can be used to make bonds. So if you're doing a symmetrical bond making process, then each atom contributes one electron to form the bond. So A is contributing one, B is contributing one to form the AB bond. If you have unsymmetrical bond making, then one of the partners is contributing both electrons to form the bond. So here B is contributing both electrons that form the bond between A and B. Remember, a bond is just a sharing of two electrons. Now, if you were paying attention, you may have noticed that I used two different types of arrows on the last slide. So the arrow with a fishhook appearance, like this, indicates the movement of one electron in the symmetrical process. However, if you have this type of arrow with a normal arrowhead, that indicates the movement of two electrons. Here's an example of a radical reaction mechanism. So in this reaction, we're going to add chlorine to methane. In the first step, which we call initiation, the chlorine molecule unsymmetrically cleaves. So then you end up with two chlorine radicals. So that bond between the chlorines has unsymmetrically cleaved with each chlorine taking one of the two electrons. Then in the propagation stage of this reaction, that chlorine radical combines with a hydrogen atom and one of its electrons from methane to form HCl and a methane radical. Then another molecule of chlorine reacts with the methyl radical from part A to form another chlorine radical and methyl chloride. So notice here that I'm using only fishhook arrows because the bonds are being broken in a symmetrical fashion and being made in a symmetrical fashion. The final stage in a radical reaction is called termination, and that happens when any two radicals combine to form a stable product. And so these would be possible termination steps. Now, in contrast to radical reactions, we have polar reactions. So molecules contain local unsymmetrical electron distributions caused by bond polarity, which is caused by differences in electronegativities between the atoms connected by bonds. And bonds in functional groups are polar. Carbon atoms bond to electronegative atoms, for example, have a partial positive charge, whereas carbon atoms bonded to metals have a partial negative charge. So here's a table of common functional groups, and the delta plus and delta minus are indicated for the various bonds. So the more electronegative atom will have the delta minus, the less electronegative atom will have the delta plus. In particular, notice that with everything with the C double bond O, the carbonyl, the carbon of the carbonyl has a delta plus. That's because that more electronegative oxygen is pulling electron density away from that carbon. Polar reactions involve the reaction of a nucleophile with an electrophile. Nucleophile is defined as an electron-rich species that can donate electron pairs to an electrophile in a polar bond-forming reaction. An electrophile is a molecule that can accept electron pairs from a nucleophile. In terms of Lewis acids and bases, a nucleophile would be a Lewis base and an electrophile would be a Lewis acid. So here's an example of a polar reaction mechanism. The nucleophile donates its lone pair to the electrophile to form the bond between A and B. Here are electrostatic maps of electrophiles and nucleophiles. So the red color indicates a buildup of charge, of negative charge. So with these nucleophiles, you have the chloride ion, the hydroxide, and the oxygen is going to be the nucleophilic atom. Then you have water with the oxygen being the nucleophilic atom, and you have nitrogen here in ammonia with the nitrogen being the nucleophilic atom, because the atom must have a lone pair to be nucleophilic. And then here are some examples of electrophiles. So for anything containing a carbonyl, the carbon portion of the carbonyl would be the electrophilic site. If you have a halide, an alkyl halide, the carbon connected to the bromine or the halogen would be the electrophilic site. And then if you have H3O+, the H atom is the electrophilic site. So here is an electrostatic potential map of boron trifluoride. Based on this, is it likely to be a nucleophile or an electrophile? Think about that and we'll talk about it in class. Here is an example of a polar reaction, the addition of HBr to ethylene. So here is ethylene is the nucleophile and HBr is the electrophile. So first, whenever you're looking at a reaction, notice what has changed. So in the reactants, you have a double bond between the carbons, but in the product, you have a single bond. So you got rid of the double bond, and then look what else happened. You've added the H and the Br to the carbons of the double bond. So this is an addition type of reaction. Now here the nucleophile is the double bond and the HBr is the electrophile. So pi bonds, the bonds that result from p-p orbital overlap, actually are good nucleophiles. So here in this electrostatic potential map you can see some red coloring. That's due to the pi bond. And so that will react with an electrophile such as HBr to form the final product. This is a picture showing a comparison of carbon-carbon single and double bonds. So with the single bond, there's no accumulation of negative charge, but with the double bond, you do see this red area here, and that is due to the pi bond. Also, something else to think about is that the pi bond, those electrons are above and below the ring, and those are more accessible, and they're also held less strongly than in a sigma bond, so they're able to be used in reactions. So here would be an example of a mechanism. So in step 1, we draw an arrow from the pi bond to the hydrogen atom, and then the HBr bond breaks. And notice we're using normal headed arrows here because we're transferring 2 electrons with both arrows. So now that's going to form what's called a carbocation, which is just a carbon with a positive charge on it. And that's going to be electron deficient. And then the bromide that was released in the first step is going to attack the carbocation in the second step. So this is a 2-step mechanism. Mechanisms can be 1-step, 2-step, they can be many steps. And both of these steps are polar reactions. They involve a transferring of 2 electrons between nucleophiles and electrophiles. So polar reactions occur by combining an electron-rich site of a nucleophile and an electron-deficient site of an electrophile. And a carbocation is just a substance that has a positively charged carbon atom with 6 electrons in its outer shell. So based on the reaction I just showed you, can you predict what product you would expect from reacting cyclohexene with HBr and HCl? So this is going to be an addition reaction, and the double bond will be the nucleophile and the HBr, or in the case of HCl, those would be the electrophiles. So here are the products. Notice the double bond is gone in both of the products, and we've added HBr to the top and HCl to the bottom. Now let's go over some rules for using the curved arrows. Electrons are going to always move from a nucleophilic source to an electrophilic sink. So the arrow starts at the lone pair on the nucleophile and ends at the electrophile, never the other direction. In addition, the nucleophilic site can be neutral or negatively charged. The key is that it must have a lone pair of electrons, or a pi bond. The electrophilic site can be neutral or positively charged. So here we see the nucleophile is the double bond, and so the 2 electrons in the pi bond are going to be grabbing a hydrogen atom from H3O+. So this is the electrophile, which I'm going to abbreviate as E+. And then that breaks the HO bond, and the 2 electrons in that bond become a new lone pair on water. Now the octet rule should always be followed, so be wary of forming any carbons with 5 bonds to them. So we use curved arrows to indicate the flow of electrons. So can you figure out how the electrons would move to go from the reactant here to the product, and also what type of reaction is this? So notice we start with 1 reactant and we end up with 2 products. So this would be an elimination. And the lone pair on oxygen would move to form a double bond between the oxygen and the carbon, simultaneously with the carbon-chlorine bond breaking, and those 2 electrons in that bond leaving with the chlorine atom. Notice when I'm drawing my arrows, if I show a bond breaking, the arrow is going to originate at the center of the bond. That's the formalism. And then if I'm showing a new bond being formed, like a new pi bond, then I also want that arrow to end at the center of the existing bond. Now we're going to move into the second part of the Chapter 6 material, which is describing a reaction using equilibria rates and energy changes. So this looks a little bit funky. Let me rewrite this. So we can describe any reaction as the reactants going to form products, where the reactants would be A and B, the products would be C and D, and then these smaller coefficients, those are the stoichiometric molar coefficients. And then the KEQ of any reaction is the concentration of the products at equilibrium divided by the concentration of the reactants at equilibrium, where each one is raised to its stoichiometric molar coefficient. If the KEQ is greater than 1, then you have more products than reactants. If the KEQ is less than 1, then you have more reactants than products. And if the KEQ is 1, then you have roughly the same amount of reactants and products. Now, in general chemistry, you learned about Gibbs free energy, which tells us whether or not a reaction is spontaneous. And exergonic reactions are reactions that are spontaneous and correlate to a negative delta G. And endergonic reactions are reactions that are non-spontaneous, and those correspond to a positive delta G. Delta G can also be correlated to the equilibrium constant that we talked about using this equation. Now, in the delta G equation, delta G is equal to delta H minus T delta S. Delta H refers to enthalpy, which is the measure of change in total bonding energy during a reaction. And there are two types, exothermic and endothermic. Exothermic, exo, external, out. That's a reaction that releases heat. Endothermic is a reaction that absorbs heat. Entropy is the measure of change in the amount of disorder. A positive entropy change value means you're increasing in disorder, whereas a negative value means you're decreasing disorder or increasing order. So here's an explanation of the delta G equation. So delta G, Gibbs free energy. That tells us the energy difference between the reactants and the products. When it's negative, the reaction is spontaneous. When it's positive, it's not spontaneous. Enthalpy, that's the heat of the reaction. When it's negative, the reaction releases heat. When it's positive, the reaction needs heat. And then entropy, the delta S term, refers to the molecular randomness during a reaction. When delta S is negative, randomness decreases. When it's positive, randomness increases. So increased randomness favors spontaneity, and exothermic reactions favor spontaneity. Which reaction is likely to be more exergonic, meaning more spontaneous? One with a KEQ of 1,000 or one with a KEQ of 0.001? So before you do the math here, you can just think about this. A KEQ of 1,000 means the reaction really favors the products over the reactants. In other words, it's spontaneous. Something with a KEQ much less than 1 means the reactants are favored a lot more than the product, which corresponds to it not being spontaneous. Now you can check this by actually doing the math and taking the ln of 1,000 versus the ln of 0.001, and you will see that if you use the ln of 1,000, you get to a negative value for delta G, but the ln of 0.001 is actually a negative number, which would end up with a positive delta G. And don't forget, negative delta G equals spontaneous. Positive delta G equals non-spontaneous. You may recall learning about bond association energy in general chemistry. It's the amount of energy required to break a given bond to produce two radical fragments when the molecule is in the gas phase. Energy is determined by the type of bond, and the changes in the bonds can be used to calculate net changes in heat. So you probably calculated enthalpies for a particular reaction by using bond association energy values. So whenever you break a bond, that requires energy, and whenever you make a bond, that releases energy. So essentially, in a reaction, you look at the difference between the bonds made and the bonds broken. If the bonds made are stronger than the ones that you started with, then you're going to end up with a release of that extra energy in the form of heat, and that would be an exothermic reaction. Organic chemists like to use energy diagrams to show the energy changes in a particular reaction. So in these diagrams, we have on the y-axis energy, so the higher up along the y-axis, the higher the energy, and then on the x-axis, we have the reaction progress. So as the reaction is occurring over time, what is happening to the energy level? And then there are a couple terms you need to know: transition state and activation energy. Transition state is the highest energy point in a reaction step, and then the activation energy is the energy required to go from the reactant to the transition state. So in this particular energy diagram, we see that we have the reactants being the ethylene and the HBr, and they're at this particular value. And then they will come up here to get to the transition state before they arrive at the carbocation product. So the transition is in between the first reactants and what we call an intermediate. A transition state structure can never be isolated. That is a structure where bonds are in the process of forming and breaking. So in the transition state for the reaction we've been talking about, the pi bond is breaking, which is indicated by these dashed bonds, and a new bond between this carbon and this hydrogen is forming, shown by this dashed bond, and then the HBr bond is breaking, shown by those dashed bonds. Every type of reaction has an energy diagram associated with it, so these would be some hypothetical energy diagrams. Notice here that this delta G has this symbol next to it. That refers to the delta G, the amount of energy change in between the reactants and the transition state, and it's called the activation energy. So the activation energy will also give you a sense of how quickly the reaction will take place. The greater the activation energy, the higher that hill, the slower the reaction. The smaller the activation energy, the smaller that hill, the faster the reaction. Which reaction is faster? One with an activation energy of 45 kilojoules per mole, or one with an activation energy of 70 kilojoules per mole? Well, the one with 45 kilojoules per mole is faster because that's a smaller value, a smaller hill to climb than the other reaction. If a reaction occurs in more than one step, it must involve species that are neither reactant nor the final product, and we call these intermediates. And each step has its own free energy of activation. So I showed you an energy diagram for the first part of this reaction, but now let's look at the entire reaction. So this would be the intermediate. It's neither reactant nor product, but it is in the middle of this reaction. So this is the complete energy diagram for the reaction of ethylene with HBr. So here on the x-axis we have the reaction progress. So this is as the reaction's happening, as the bonds are being made and being broken, what is happening energetically. So here we have the reactants at this level of energy. Then we have the activation required to get to the first transition state, which then forms our carbocation intermediate. And then we have another activation energy, another hill to climb to get to the final products. So notice the difference in energy between the final product and the initial reactants. That's the delta G of the reaction. So if that is negative, so if the products are lower energy than the reactants, then it's spontaneous. So this is a spontaneous reaction. The delta G of activation, the activation energy, is always going to be positive because it always requires energy to break bonds. And then the hills in these energy diagrams are always the transition states. So hills are transition states. Any valleys you may see would be the intermediates. Finally, I want to mention a comparison between biological reactions and lab reactions. Laboratory reactions are often carried out in an organic solvent, like dichloromethane or acetone. Biological reactions occur in the aqueous medium inside of your cells, and they typically involve an active site, for example, a pocket in an enzyme where a substrate is bound and undergoes a reaction. This is an example of a biological reaction, the conversion of glucose to glucose 6-phosphate in the presence of hexokinase. This is a picture of hexokinase, and this is the active site where the glucose is transformed into glucose 6-phosphate. So in summary, The four types of reactions are addition, elimination, substitution, and rearrangement. A mechanism describes how a reaction occurs, and the mechanisms by which most reactions take place are either radical or polar. And polar reactions are the ones we're going to see a lot more of in organic chemistry. And those occur between a nucleophile and an electrophile. The position of a chemical equilibrium is determined by the value of the free energy change. And enthalpy and entropy are terms that tell us whether or not something will be spontaneous. And enthalpy refers to the net change in the strength of chemical bonds broken and formed, and entropy corresponds to the change in molecular randomness. Exergonic or spontaneous reactions have negative values of delta G. Reactions that are endergonic or have positive values of delta G are non-spontaneous. Then we also looked at energy diagrams, which describe the energy changes as a reaction proceeds. And the transition state is an activated complex occurring at the highest points, at the hills in the energy diagram. And those cannot be isolated. Those involve bonds in the process of being made and being broken. And the amount of energy needed to reach this transition point, this transition state, is called the energy of activation, or the activation energy. And it's represented by delta G with this symbol. And reactions can take place in more than one step, and if they do, they will involve the formation of a reaction intermediate, which is neither reactant nor final product.